Hello, everyone. My name is Tobias Ternström, and I actually not too long ago joined AWS, and I lead product management for our relational database service, RDS, and Aurora, our cloud-native relational database service. And so in this talk, we will spend some time, I thought, in the guts of Aurora and see a little bit how things work. Mostly interesting since I have recently learned it myself. So then I can kind of give you guys these my learnings. I have spent some time on SQL Server in the past. So it's been exciting to learn some new stuff. I also have Jimbo here from our team, so that if there are any questions at all, Jimbo can answer those. Cool. So let's see if this. Oh, clickety thing. Turn on. There we go. So first of all, silence cell phones. Don't forget to put your session evals in at the end of this. And the agenda is we're gonna start by just very brief overview of what we do in relational in AWS, and then quick recap of how databases work. I was thinking all of you guys might need that, and then a bunch of stuff basically after this. I was meaning to have a proper agenda, but it took a while, so then it's just a bunch of stuff. Anyway, Amazon Relational Database Service is our database service for all of you who want a fully managed relational database experience in the cloud. And we basically want to provide you the choice of database. So we support our own fully MySQL and PostgreSQL compatible versions through Amazon Aurora. We run the open source bits for MySQL and PostgreSQL as services. We have MariaDB, and then we also offer Microsoft SQL Server 2012 and onwards as a service, as well as Oracle as a service. So it's kind of a complete offering, and you pick the database of your choice, and we provide it fully managed. It's a popular service, as you can imagine. Relational databases haven't gone out of style yet, so 70s is still going strong. We have actually hundreds of thousands of customers running RDS today. In terms of Aurora, what is that? Well, the thought is, and I think this is a somewhat beautiful statement, it's MySQL and PostgreSQL compatible relational database built for the cloud with performance and availability of commercial grade databases at one-tenth the cost. That's kind of the promise of Aurora. And the thought is, if you built an app on MySQL or PostgreSQL, you can run it on one of those two distros, or you can just point your app at Aurora and it will just work. Okay? And obviously, if you want to run your app somewhere else, you can run it anywhere where on-premises or some other cloud where they also support MySQL or PostgreSQL. But we do this while providing you the high availability, the ease of use that you expect, the performance that you expect from commercial grade databases. So, enough of that. Let's get into first a little bit of this recap of database internals. And first of all, what is it that we care of in a database generally? We care about the transaction log. And the transaction log is what it's called in SQL Server. In other databases, it's called somewhat different things. For example, here we call it a write-ahead log. It all means the same thing. And what is the transaction log or write-ahead log for? Well, it's to provide a do, undo, redo protocol. So you have some state of the database, you do something, you produce the new state, and you produce a log record that goes with it. And the thought is, by using this protocol, you can go from new state to old state, meaning you can undo something if you need to, so roll back a transaction, for example. Or you can redo something, or sorry, old to new. You can redo something, such as in case of crash recovery, or you can undo, go from new state to old state. That's the whole point of this protocol, and that's the whole point of how Aurora was built. Basically the thought that the log is really the database. So if you take this example, just again to get us started, so here we have 4 transactions, and in database terminology, I think we all probably know what a checkpoint is. So a transaction in a database generally works as the app sends it in, the database does the update in the buffer pool, in memory, generates the log record, and writes the log record to disk. Okay? This means that if the database crashes, when you come up, all of the information you need is always in the transaction log. But the actual data pages that store the database itself may not be up to date because all of the information was written to the buffer pool, but it hasn't been written to disk yet. So generally you have 2 types of processes that update the data pages of a database. One is checkpoint, and the reason for having checkpoint is, well, if I need to bring the database up again, then anything that's not already in the data pages, I need to redo, right? I need to go through recovery. And the recovery can take some time. And obviously, the longer time it takes, the more you have to wait until your app is available again. Okay, so one reason to refresh is checkpoints, so a database generally as frequently as possible, checkpoints to make sure that the database pages are up to date. So when it starts up, it can recover quickly. But there are also other reasons to write to disk, such as the buffer pool or the gets full and needs to flush pages to disk. So that's kind of the 2 reasons to write data pages to disk. So if you look in this example, we have the transaction 1 through 4. We have a checkpoint here at time C, and then we have a system failure here at F. And in this case, when the database comes up again, it knows that everything before the checkpoint are written to disk and it's safe. And after, it's not. So it needs to go through the log and make sure, it could have been written, right, but it's not sure, to make sure that everything is correct. So in this case, transaction 2, it needs to redo part of transaction 2. It needs to redo full transaction 3. And then transaction 4 never committed. So it needs to make sure that one gets undone, because some of the pages might have gotten written to disk. Okay? So this is kind of the basics of database crash recovery. So what about creating a cloud-native database architecture? So first of all, I/O is critical to databases. We all know this. So as long as you're writing to a database, you have to make sure that you can write those pages fast enough. And also, if you read a lot, you need to be able to read those pages that you need fast enough. So the general principle for the last 40 years or so is you want to increase the bandwidth of I/O that you can support, and you want to reduce the amount of I/O that you do. That's kind of the formula. And generally, this has been done with direct attached storage. That's the traditional way of doing this, right? There's hard drives attached to the compute node that runs your database. In the cloud, all of a sudden, we generally have a separation of compute and storage. And generally in the cloud, you either have network-attached storage. So in AWS, we have Elastic Block Stores, EBS, that you can attach to any VM and use. Or you can use local disks on the compute node. The problem with using local disks is that the compute nodes can go away at any point in time. They fail, and then you lose whatever data was on those disks. And this is generally something that you do frequently on premises as well, with something like a SAN or a NAS architecture, where you have separated storage and compute. Now, the problem with this is that your I/Os tend to become slower, or that you share your bandwidth with more other compute nodes. Okay, so you need to make sure somehow that you can get the performance out of this. So what is Aurora? So our Aurora took the approach of completely separating compute and storage and building microservices architecture or service-oriented architecture where we have compute nodes that run the actual database engine, we have then storage nodes that run, you can argue, part of the database engine, because it needs to understand the database engine's log and page. And those storage nodes, those have to be guaranteed to always be around. Those have to make sure that you don't lose the data, okay? But the compute nodes, they can go, you create a new one, you fail over, you create a bunch of read replicas, you get a bigger one, you get a smaller one, so on and so forth. But the storage nodes are always there. And the thought behind the storage node is if you create a big fleet of these and make sure to distribute your data across them, you can use the storage, the SSDs on these storage nodes to get some impressive results in terms of especially write performance and throughput. So how is Aurora set up? So this is kind of the first level of picture you would look at. So first of all, Aurora always uses 3 availability zones to run the system. And it's always the storage nodes that are across 3 availability zones. You can run any amount, 1 or more compute nodes, but the storage nodes are always across 3 availability zones. What's an availability zone? An availability zone is generally a data center. So each availability zone is a data center within a region, within some metro area. And there's a bunch of thought that goes into how separated they need to be depending on what kind of issues you can have in a certain region. So there is no general rule of they are X miles apart or anything like this. But generally, they are multiple data centers within a region. And when you create an Aurora instance, you get 1 compute node that sits in some availability zone. And then we go and use or allocate segments across a multi-tenant storage system. So this multi-tenant storage system is a bunch of thousands of storage nodes, and each storage node can basically take log records and produce pages. That's basically what each storage node does. But it's a multi-tenant system in the sense that it works kind of like, you imagine S3. You don't have a specific machine that's your machine. You send all of your data into a big data lake, and then you store it there. So you can look at this similarly. Bunch of machines where you store your data. But the trick here is that it's a database optimized storage system. So it understands database pages and it understands database log records. So for example, Aurora supports MySQL and PostgreSQL, both of them, which means we have storage nodes that understands MySQL pages and log records of various versions, and we have storage nodes that understand PostgreSQL log records and pages, if that makes sense. Anyway, so once you create an Aurora instance, you have the compute instance. That's basically the standard database as you would imagine. It runs your SQL transactions, buffer pool, all of this. But the storage is managed by this multi-tenant system. And then whenever you store something on this system, it's stored 6 ways. So across this system, you basically create something called segments. So a segment in Aurora today is 10 gigabytes, or up to 10 gigabytes. So if you would imagine the minimum you could have is 1 segment. Now we create multiple segments even for an empty instance, but if you think about it that way. So when you create an instance, you create 6 segments across 3 availability zones. You write a record, then that record will be replicated 6 ways. So 2 copies in each availability zone. And we'll get into why we do 6 ways instead of 3 ways. If you look at now the I/O profile and just compare it to MySQL, I know most people here are SQL Server people. It's similar in SQL Server to some degree, I would think, as in MySQL. But some nuances, I'm sure, are different. So on the MySQL side, whenever you need to write, you can see all of these arrows with different colors. Down here we have at the bottom the legend for these colors. So the green arrows mean it's writing, the database is writing a log record or log. Yellow here is bin log, which in MySQL means it's the information around what command was executed plus some data structures related to this. You have the data, updated data pages such as checkpoint. You have the blue one, double write. So MySQL does this to make sure that you don't have a torn page. It writes it twice. Okay? And then you have this purple arrow, which is writing FRM files. It's metadata related. So as you can see here, in MySQL regular, you send a write in, you will generate at least one of each of these, right? You write some metadata, depending on what you do. You don't always need to write metadata, obviously, but you'll write to the data files when you checkpoint, you'll write log for sure, you'll write bin log for sure, and then if you do replication, you'll replicate all of this over to the other instance, and it will do exactly the same thing. So you generate a ton of I/O. On the Aurora side, it's different. So you can see here on the Aurora side, we have a primary instance and then up to 15 read replicas of this instance. But if we ignore the read replicas for a second, the write comes into the primary. It generates the log record for this, just as MySQL would do. But then it sends the log record down to to all of the 6 storage nodes that it needs to talk to. So it needs to figure out which segment do I need to write to. So it has some geometry to figure out where is this segment. So which storage nodes do I need to talk to? This head node knows that. It sends this to those 6 storage nodes. And those storage nodes apply this, send back an ACK with a bunch of information. We'll get into some more of the information it sends. The primary instance also sends it to all of the read replicas. But the read replica, we also only send the log. Because the interesting thing here is the read replicas all use the same storage as the primary. There's no separate storage for the read replicas, which means in the MySQL case, you'd have to write it to the other side. Most replications, the databases where you do replication. But here we don't, because if the read replica needs a page that it doesn't have in memory, it just goes and asks the shared storage. Okay? So why does the primary node send anything to the read replica? Well, the read replica also has a buffer pool, right? So you have to make sure that that buffer pool gets updated, because otherwise the read replica could serve information that's old. Okay, so that's the only reason it sends it to the read replicas, is to update the buffer pool. The read replica never writes anything as it gets the replication from the primary. And then you can see this red arrow, data pages. So on all of these storage nodes, it gets the log records in. Over time, we'll get into some details, it generates the actual data pages from these. So why does it need to generate the data pages? Well, if either a primary node or any of the read replicas need the data page later, it'd be expensive to go through this redo protocol all the time for all of these log records. So we generate the data pages, we store them on the SSD, and then every once in a while, we ship these off to S3. So S3 is just blob storage. And why do we do that? Well, this is for backup. So if you want to recover, if you want to do point-in-time recovery, you want to keep long history of this. And that's what we use S3 for. Make sense? So what happens in terms of performance? Here are some benchmarks. These are SysBench benchmarks, right, Jim? Yeah, SysBench benchmarks. So you can see on the write throughput, Aurora is quite a lot faster than regular MySQL. And this is the same setup as we saw on the other page. And not with a read replica, actually. It's just a single AC for regular MySQL. And on the read throughput, it's somewhat faster as well. So let's get into a little bit more details around how this actually works. So the log is the database. I think everyone kind of gets why we're saying now the log is the database. So just going through this, so the database instance writes redo log records to storage, meaning it sends it down to Aurora storage. The database instance reads pages on demand for storage, which uses the same redo log applicator as the database instance to produce the correct page image. What does that mean? Well, so again, if any read replica or the master needs to read a page, that page can be in one of two states. It can either be not a page yet, because all we have is it's in the buffer pool on the master, right, and possibly the replicas, but it's only log records been written to disk so far, or been written in the storage tier so far. Or it has become a page. And this becoming of a page, we'll see on the next slide, but that is what needs to be the same code as on the database instance. right? They need to always be in sync. So you need to make sure that whatever log records turns into pages on the storage tier, that exact same thing has to have happened if this happened on the database tier, right? Because the database would have produced this exact page and shoved it into the buffer pool. Yeah? Oh, I have a rule. Only easy questions. If it's very easy, you can ask me. If it's, it's very easy is easier than super easy though. But okay, yeah.
How's the buffer pool being replicated to reading replicas?
Oh, it's a good question. So how are we replicating the buffer pool? So as I mentioned, you generate a log record on the primary, right? And you send it off to these 6 storage, you figure out which storage nodes are involved, you send it to those 6. At the same time, you also send it to the read replicas. So when I send this, so then the read replicas have to apply this, right? So they also produce the page in the buffer pool on their own.
The same one as the master.
Exactly, the same one, but delayed. The master won't wait for the read replica to be done with this, right? So the master will be slightly ahead of the read replica.
So the transaction can already commit it in the primary, right? And it's not going to wait until
Exactly,
somewhere in
yeah.
the background. So
Correct. We'll see what happens.
The page is not in the buffer pool on secondary. Would it be loaded when you apply the log? So when you send the log record?
Sorry?
If you send the log record.
So the question was, if the page is not on in the buffer pool of the reader, do we load it? And the answer is no. And Tobias will get into that when he talks about replication. But we only apply the buffers on the readers if it's already in the buffer pool. Otherwise, you may never need it there, and you wait for the reader to pull it when you run a query. Right? So it's just going to toss it away.
Yes, question.
So if a read replica hasn't yet received the log, how does it know that it's not in sync with the primary?
Oh, it doesn't.
So it'll just, so it's a...
It knows. We'll get into. I think once we go a few more slides in, I think you'll see. But it doesn't know.
It's just like snapshot almost.
Yes.
Send it
Not
until
in
after it
real
gets the
time.
acknowledgement back from storage.
Yes.
That it's persistent.
Correct. So, I think this is what we have a few slides that gets into this. This slide is my favorite because it's so easy to understand. You just look at it and you're like, this makes total sense. This is irony. I'm from Sweden, so we use a lot of irony. So anyways, so first of all, this white box over here, database instance. So this is this compute node that's taking all of the writes. And then we have one zoomed into one of the storage nodes. So for any single write, there will be 6 storage nodes involved. And then we have another storage node, another of this guy's buddies hanging out here, and then S3 here for backups. So let's look at exactly what happens. So this writer comes in, a log record is generated, however it got generated, it got sent to the storage node. And first of all, one thing that's somewhat interesting here. So when do you talk to the storage node? So if you take a regular on-prem database, so when does it send something to disk? Is it, so there are 2 types of things, right? There's the data pages. So those are written either at checkpoint or because the buffer pool gets full and needs to flush stuff out to free up, okay? Then you have the log records. So those get written for one of 2 reasons. Either you commit, right? Or there's a buffer in memory, a log buffer that you keep writing to, and that log buffer gets full. And then you need to flush so that you can make room for more. The problem here is that you need to make sure that you don't speak to the disk too frequently because it's very expensive. It's very slow. Like this is one of the first slides, right? You want to have few IOs. So databases have this thing called group commit. So we have a guy commits, but maybe there's not all that much in the log buffer. The database will wait a bit for the log buffer to get to some reasonable size before it sends it to disk, okay? Here we have a difference because here we're not waiting for to get an efficient write to a disk. We're going to do just network I/O from the database side. So we have the same kind of thing in Aurora where there is a buffer that gets filled and needs to get flushed, but that buffer can be much, much smaller. than when we're waiting for disk. Because network I/O doesn't have the problem of you have to send a certain size, right? So the storage node gets the log records. And again, there can be multiple storage nodes that get this log record. It's not necessarily one storage node in a transaction. So this gets fanned out to whatever number of storage nodes need to get included. And as we go, so I could start a transaction, do a bunch of insert, updates, deletes. As I go through this transaction, these log records get generated and they get sent to storage. Not maybe immediately because there's some buffer to fill, but they fill that buffer and it gets sent off. Don't have to wait for commit. Okay, send them off, they go into the storage node, and at some point the commit also gets there. So we're asynchronously sending everything to the storage node. Okay, make sense? So it comes into this incoming queue, lands in memory on the storage node. One thing that's interesting with the storage node, it's completely now self-contained. It doesn't know anything about it doesn't care about the outside world. It just acts on its own state. It gets a bunch of information from the database instance. It has a bunch of information about what the world looks like, such as which log sequence number we are at for a certain thing. But this guy, it just has a fairly simple task. So it gets these incoming queues into buffer pool. The first thing it needs to do is it needs to guarantee that these have been written, right? Because otherwise, the log record is useless. So it goes to step 2. It writes the log record to disk. And again, because the database instance sends to many storage nodes, we're now amortizing all of this work, right? So many storage nodes take it into their buffer pool. They write it to disk into what we call the hot log. As soon as it's been written to the hot log, the storage node tells the database server, I'm done, okay? And by the way, with each of these log records that we send a bunch of information about the state of a database. We'll come to that in a later slide. So it sends it. The database node then knows, that 1 out of 6 storage nodes act my log record, right? And then basically when it reaches commit, it just needs to wait for enough of these storage nodes to have caught up, if that makes sense. So as long as 4 storage nodes, 4 is quorum here, as long as 4 storage nodes have gotten back and said, I've written everything, then the database instance can move forward. So you see how we're amortizing this. Rather than buffering everything and then sending a big thing once in a while, we send it all the time and amortize it across a bunch of nodes. So then after this, so again, after step 2, the database instance isn't waiting for me anymore, but I have some more work to do. So then it goes into the update queue. And what is this update queue? Well, after this update queue, and I'll take step 4 in a while, we need to generate the data pages, okay? Again, why do we need to generate the data pages? Well, because the primary might read them later when it's not in the buffer pool or some read replica needs them, so we need to have them ready to read. But I can't generate the data pages if I don't have all of the log records before. So since things come into the incoming queue and we just try to write them as fast as possible, we may write them out of order, right? So each log record has a log sequence number. And the log sequence number is owned by the database instance. So it generates the number, and then it goes. So it might have written log record 4, but log record 3 is still not written. So I can't go generate the data page until I know that the log record behind me has been written. So that's what happens. We put them into this update queue. And so the goal of this stage is make sure it's durable. The goal of that stage is make sure there are no holes before me, okay? As soon as I get to there are no holes before me, this is what we call the segment complete LSN. So segment is complete until my log number. Then we go and create the data page. So now we update the data page. We can write that data page to disk, and it can be served for reads. So an obvious question here is, what if I'm unlucky and some read replica comes in, or someone comes in and wants to read this page, but we haven't created it yet? Well, then we have to create it. So then we go, okay, fine, I'll go create this, and it has to wait until I've generated this page, okay? By the way, as soon as I reply back to the database instance, I'll tell it what log record am I on. So I'll say, I am, segment complete until log record 56. So now the database instance know how far I am at catching up, okay? So then what can happen obviously here is that I may find that I'm missing a log record. I'm like, okay, I'm on 5, this 4 thing is nowhere to be found. Don't know why this happened. So we have a gossip protocol, which means I go ask my buddies, hey, do you guys have this page? And they go, oh yeah, or it's not exactly, that's not exactly a protocol. It speaks Spanish actually, so it's, no, hola, ¿qué tal? No, it's late in the day. What it needs to do is it just says, hey, this is how far I am with my segment complete. Where are you guys? And they'll go, okay, I'm further ahead. And then it can go and ask for those pages. So they keep gossiping with each other to get forward as fast as they can. Because we have this 4 out of 6 quorum, it's not sure that it's the same 4 out of 6 all the time. I just switch sides. Don't like the podium. Okay, so we handle the 5, which is the writing the page. Again, the step 6, periodically we'll take those pages and log records and send them off to S3. And again, that's for handling Pitter. So I can run the whole system except for backups without S3. I don't depend on S3 to serve traffic. But then, given that I keep generating new page versions, note I don't overwrite data pages. So a new page gets generated, I store it. At some point, I need to remove data pages. So that's the garbage collection. And then also, we periodically go and validate, do cyclic redundancy checks on these pages to make sure that everything is in order. Because if I find a page that's not healthy, I can just go ask my buddies and say, like, ooh, I need this page. It's not healthy. Okay? Any questions on this? Yes?
Is everything you're saying true for Postgres as well as MySQL?
Yes, yeah, it's the same thing, except it's a different page, it generates pages differently and all of this. The page size in Postgres is, I think, 8K, right? And 16K in MySQL. Yep.
How do you handle, like, I guess if someone calls a begin transaction and you start writing, and it starts getting into the hot log, and then there's a rollback. Does that then just write new pages?
We'll get to that, but we don't have to care because it will need to generate this transaction just never committed, so that's fine. Yeah.
Database engine itself that handles the transaction management. This is storage.
Yeah.
A hard drive wouldn't know about your transaction state. The database engine manages those transactions.
So we'll later.
So it's not writing any log records basically until
It's writing the log records as if you were writing it out to the local drive. Right? And it's getting down there, and it's like, so as far as transaction state, whether or not that transaction has been committed or rolled back, the database engine itself knows the state of that. So like in Postgres, there's a separate commit log that has the state of the transaction, whether or not it's been committed or rolled back, and reconstructs the version of the page that goes out.
Yeah.
it is a reconstruction.
Yep. Yeah.
Okay.
So, durability at scale. So what about these failures? So now we have kind of roughly how it hangs together, and we'll get into some more details. But what about these independent failures? So this is kind of the classic design that you think about when you think about availability zones. So I have 3 availability zones, so I'll spread my data across the 3 availability zones. Why do we do 6 replicas? Well, the problem with this is it can only handle 1 failure. So if 1 disk or something goes out, it can handle that, but not 2. So you think, okay, but that's fair. The problem here is if an availability zone goes down, right? Now all of a sudden, it's very dangerous because I cannot handle any more failures until I've recreated everything in that, made a copy again of everything in that availability zone. So this is why we do 6 copies instead of 3. So in this case, losing this pinkish thing, now I have data loss. I can't recover from this, okay? Unless my availability zone comes back and turns out to be fine. But otherwise, I've lost data at this point. So how do we tolerate this? Well, we write instead 6 ways. So now, if 1 availability zone disappears, I can tolerate 1 more failure. Like 1 segment more I can lose, and I can still continue going. Okay? Or rather, I don't have data loss at this point. Okay? So how do we, what do we do? So write quorum again is 4 out of 6 have to always acknowledge. Okay? Read quorum, we always read from one of the segments for standard traffic. But what if this AC plus 1 thing happens? So if I have lost one availability zone, this is obviously very, very rare, and I also lose one more thing, then I still have exactly the data I need. Now I need to make sure I don't lose another one, because then I have data loss. So then immediately what we do is we rebuild the failed node so that we're back to 4 out of 3. So while we do this, you can still accept read traffic, but we do not accept any more write traffic. Okay, so we're in this semi-suspect state. And so how rare is this? Well, this is basically a function of, so mean time to failure, MTTF. You can only reduce this so much, right? The mean time to failure. So it's at some point it's hard to control. But what we can do something about is how quickly can I recover? So the thought is here, if this very unlikely event, I lose an availability zone and I lose one more thing, how long am I now in this risky state? So this is basically a balance, and it's a balance now of how big segments do you create? Because if you have lots of little segments, it's riskier. It's a higher chance that you will lose something. But the nice thing with the itsy bitsy segment is I can recreate it quicker. I can copy it from somewhere else quicker. So I'm in high risk for a lower amount of time. So this is one of the key reasons why we have this 10 gigabyte segment size in Aurora. Because of the fact that if this happens, I need to copy 10 gigabytes. And on a 10 gigabit network, it's basically 10 seconds. So I have 10 seconds of higher risk. And this is where we've concluded this is a very, very, very low risk. Okay? And if something like this would happen, then the second after that, in this extremely unlikely event, then you have in S3 backups. Right? There continues. So back into this segmented storage. So again, in Aurora, we create segments. We allocate a bunch of segments at a time, and we throw these segments, we allocate them over thousands of nodes. So you shouldn't think of it as like I have 6 storage nodes that hold my database. Right? It's many, many, many storage nodes that have different segments, different 10 gig segments of my database. And each segment is replicated 6 times. Okay? And this set of 6 segments together. So a segment in Aurora speak is a 10 gigabyte thing today. Then the 6 together we call a protection group. So this is a group of 6 together that are there to protect this data. And again, like I talked about, there's a trade-off between the likelihood of faults and the time to repair, and this is where we landed on this 10 gigabyte size. And so chose the biggest size that lets us repair fast enough, right? So resilience and operations, this is another benefit. Obviously, when I now have this storage, lake of a bunch of storage nodes, I can do many interesting things because of the fact that they share the storage. So for example, I can upgrade and manage the fleet without losing quorum. Right? I can manage one storage node, if you will, at a time. I can service one AC at a time and things like this. I can do heat management. So we do things like this segment gets very hot, right? Or rather, this storage node is getting hot. Then we offload, we move segments to other storage nodes. So we continuously keep it at a level where we have very, very low latencies. By the way, it should be clear, Aurora is optimized for throughput. So where it shines is you write a lot to your database. Read throughput, we have done a bunch of optimizations in both PostgreSQL and MySQL to make reads faster. For example, in MySQL, we have parallel query. PostgreSQL has parallel query built in today. We can push predicates down into the storage layer and so on and so forth. But you pay a penalty given that you're still doing a network hop, right? So extremely low latency, you will serve from a local SSD. That's obviously going to be faster. But write latency especially if you look at it in terms, write throughput, it's very, very good and extremely consistent on Aurora. So, so what about memberships? So for each of these protection groups, and again, each protection group is a set of 6 storage nodes, but all protection groups are not necessarily on the same set of 6, right? So what happens as we move in time, so in this epoch 1 here, we have all 6 nodes are healthy, or all 6 segments are healthy. Then something iffy happens with node F, so the database instance notices I keep not getting answers maybe from node F. So then what we immediately do is we say, okay, or after some little point in time, we wait and we say, okay, let's get a new one. So we add another one to this quorum, or to this set. So now I have node F and G together. And then, and the database instance keeps writing to both of them. So now it has 7 that it sends information to. And then at some point we then decide if F is going to be healthy, then we can continue with F, or we replace F with G. But the interesting thing here is this is all decided all the time by the database instance. It doesn't need to, there's no consensus here. Someone should answer. So there's no consensus between these. The database instance keeps making the decision about who are the storage nodes in this particular protection group. So it's not one of these protocols where these guys have to decide together, if that makes sense. So yeah, so it says membership updates, they occur without consensus. The database instance just decides, and it continues, just like it keeps generating log records. I'm maybe too far away. Like a tiger. Oh. There we go. Continuous backup and snapshot. Where do we get? Yes. So about the backups. So again, we keep sending log records, and we send snapshots to S3. So snapshots of a set of pages together, copy to S3, as well as log records as are generated. And this is a continuous thing. So every now and then, send them off to S3. Which means if you ever want to do a point-in-time recovery, you can recover, and some of the data will be in S3, and some of the data will sit on the storage nodes. And you configure in Aurora how far back you want to keep these. Today, Jimbo, I believe it's 35 days today, right? So for a point-in-time recovery today, you can keep 35 days. Snapshots, you can keep longer. You can create a snapshot, and then that one just stays, and you can recover that later. So what about commits? So distributed commits. So again, the storage nodes, they establish compact consistency points by increased monotonically and are continuously returned to the database. So again, these storage nodes are not aware of what's going on around them. They just keep getting these log records from the database instance and keep applying them. So one question that you might have is, so the log records come in to this incoming queue, we write them to disk, and then we have this thing, this update queue business, which was to make sure that there are no holes in the chain. So how do you do that? Because I can't actually look if it's log record 5, then the one before me should be 4, because this is log record 5 for whatever page that I serve. So it could be that the log record before me is in some other page, or poked around with some other page, and that is on some other storage node. So the log record before me, but I'm on 5, but the log record before might be 3. So how do I know that? Well, each of the pages and log records, when we send them to the storage node, it has a backlink. So it tells, you are 5, and actually the guy before, that one is 3. So as it goes through this update queue in order to generate the pages, it knows what the chain is. So it knows what are actually holes, if you will. So it's not that it's the same contiguous range on each storage node. The only thing that's contiguous is, from the database instance perspective, it's always contiguous range, no holes. Except after a crash, we do a little bit of a jump. Okay, and then the database nodes, They manage all of the traditional things, so locks managed in the database node. We've done a bunch of optimizations around MySQL's lock manager to make it use lock-free structures and things like this. Deadlock detection, constraints, all of these things run exactly as you would imagine it from the database node. Again, the only thing that's specific to the storage here is whenever you send to disk. That's what these guys are. So, so this is, we have, I see there's LSN galore in Aurora. Many an LSN, log sequence number. There's an LSN for every which flavor. If you like LSNs, cupcake LSNs, we have cupcakes LSNs. We have Fanta, Pepsi, all types of LSNs. It has been interesting as I'm getting teaching myself. So, what are all of these things? So these things are different, basically watermarks in the log that we keep track on for different reasons. And these are some of them. This is not all of them. But so segment complete LSN. So why is this interesting? So also again, when the storage nodes act back to the database instance, it sends a bunch of these things that it knows about. Like, hey, this is the latest, for example, segment complete LSN from me. So that the database instance knows the map and understands what the state of each storage node. So segment complete LSN is the highest LSN in the for this storage node, this segment in the storage node that has no holes, right? So we know that up until this point, I have the whole chain. So there could be LSNs in front of it that are written to disk that are in this hot log, but there are still missing holes. So it's not safe to assume that all of the data is there. So it keeps telling the database instance, this is where I'm at. Okay, so the database instance knows. And again, the main thing that this is used for is actually when these guys talk to each other. So it sees I'm at SCL something, and then it asks its buddies which SCL they are at. And they kept, because they're in the same protection group. And then they can send pages that this particular machine is missing. Then we have protection group complete LSN. So this is just all of these across these 6 segments. What's the 4 segments together, the quorum highest LSN? So that can be lower than one of the segment complete LSNs. Because one of the segments has finished without holes a little bit in the future, but across 4, we might be a little bit behind still, right? And we need to keep, And then we have volume complete LSN. So this is across all protection groups. What's the, again, complete chain of log sequence numbers? And this is important for things like, the protection group LSN, for example, readers might need a log sequence number. So this I can use to know if I can clean up things, for example. So there are things where I don't advance the log sequence number because I know there's a reader that needs it. It may not have been written to S3, for example. So I keep track of all of these things. Then we have consistency point LSN. This is the last record with no holes and so on behind it that has a commit. So either it's a mini transaction, like a page split or something like this, or it's a user-defined transaction. And then you have the volume durable LSN. So this is really the key from the database instances perspective. This is across the whole volume. What's the safe, fully committed state, right? So this is what transactions will be waiting on, this LSN number to be increased. And also the database instance will send some of these, as you can imagine, the volume durable LSN, the database instance knows, right? Each storage node doesn't know because it's managing its own state. So it will be sending this to the storage nodes so they know that there is activity. And we have some special activity to make sure that even if nothing happens on the storage node, they get a little bit information every now and then. So yeah, like I said, so commits in Aurora. So when the database can prove that all changes have met quorum, again 4 at least, and it does this by ensuring that this VDL that it gets back, or that it calculates, is greater than or equal to the commit LSN that each transaction is waiting on. So again, if you go back to what we talked about before, kick off bunch of transactions at the same time, they just write, send it off to all of these storage nodes, waiting on things coming back. And then we're now waiting, can I allow this transaction to continue because I got the commit? Well, what that really is that commit has an LSN, right? So all it needs to do is sit there and look, what's the volume durable LSN at this point? Nah, it's still below, it's greater than or equal to, you can continue. Make sense? So again, no flash, there's no consensus required because the database instance decides. We'll get to crash recovery. So here's just an animation, so log application in action. So here we have transaction 1 pokes around with page 1. Again, the database instance sends it to all of the replicas. In this case, we have 1 replica. And again, that's to either update the page in cache, or like Jimbo said earlier, if the page is not in cache, the replica can just throw it away. It doesn't need to do anything. And then sends it to these 6 nodes. Again, has to make sure that there's this quorum business. So at this point, if both of them read, they'll read the same thing. Okay? Woo. So later now, so we have now T2 and T3 have been written. And from a master perspective, it sent this off to the replica. But the replica hasn't moved forward yet. Okay? The replica, because it gets a bunch of to-do stuff, and it starts doing it, and it may take it some time. And again, the primary doesn't wait for all of the replicas to acknowledge, right? It just goes. So when you read on the master right now, you'll read whatever how up-to-date the master is, so this VDL business. Whereas if the replica reads, it will only read as far as it has applied. But because of the fact that the applies are very, very fast, again, because it doesn't need to write anything on the replica side, it either needs to throw away the log record because that page wasn't in the buffer pool, or it needs to update the buffer pool. So at some point, the replica catches up and it reads the right page, or the same page rather as the master. But this is also why we need to keep the different versions of the pages around. And generally, the replica is in milliseconds behind, something like 20 milliseconds behind. So what about crash recovery? So in this case, we have this stream of log records. This VDL is here, volume durable LSN, because, and again, but volume complete LSN is 2 steps ahead. So what was the difference between these? So volume complete LSN, it's durable, it has been written. So this comes back to your question in the front row before. So it has been written to disk, right? It's in the hot log. And it's complete and all of this, right? There are no holes behind it, but there's no commit, right? The last commit that we have is this volume durable LSN. So in this case, you would go and throw away those 2 log records, okay? There is a bunch of interesting things that we do here also where if there are gaps, it might be across a couple of nodes. It might be only one node that has had the log record. So this is one thing that's somewhat interesting to note. So you send a commit to a database. It's not committed just because you got the ACK back to the app. It's committed then when the database has managed to guarantee durability. This means that the database can manage to guarantee durability, but you never got an ACK back because that could have been lost on the network or something like this, right? This also means that we may have gotten a bunch of log records in, and we didn't manage to get quorum and so on, and then the database instance crashed. So when we do recovery, we'll go and look, oh, there's one over here, there's one over there, and we'll actually go and try to reconstruct things across the storage nodes. And at some point, we've created the full thing, and then we can actually move VDL forward, right? Because we had all of the log records that were needed, right? And then so you can have moved ahead further than what the database instance knew about. And that's why when you start up, we have metadata in S3, in DynamoDB, so it knows which storage nodes to go talk to. It goes and asks them where they're at. Then they start running, and at some point you get back, the database instance talks to all of these guys to figure out now what is the right VDL. That makes sense. Again, many of these LSNs. You also get very, very fast crash recovery because, again, on most databases, when you start up, you have to go through and execute all of these log records that were since the last checkpoint. Whereas in Aurora, you do kind of the same thing to some degree, but now you may have 100 storage nodes that at the exact same time can go and do this, right? And again, they don't need to ask each other for anything other than pages. They do gossip and it's like, oh, I didn't find this one, do you have it? Or this log record. So very, very fast crash recovery. You need to get an instance up and running, and then off you go. So in terms of recovery, there's some amount of time for failure detection, so somewhere 15 to 20 seconds. You start doing DNS propagation. There are client libraries that you can use that doesn't rely on DNS propagation, where the client library knows about the nodes where you could fail over to. You recover, and then you're up and running. And in Aurora today, this is something like, as you can see here, between 15 and 30 seconds for a failover. The final thing I want to mention, we have some more time. We're until 4:30, right? Yes, perfect. So now what happens after a typical crash? So it crashed here, took some time, figure out, oh, it crashed, we need to recover. And then at some point we recovered and we're up and running again. Any ideas why does this, so that you can see this is transactions per second on the y-axis here. So why doesn't it go full throttle again? Why does it?
Because it doesn't have the full log to be built. It's doing all that work first.
Good question. So one thought is it's because it has to run through the log records. Not in this case. Doesn't have to run through the log records because that's already done. It did that on those few seconds while it was down. So as soon as that's done, it's ready to go. The problem is that the buffer pool is cold, right? So there are no pages in the buffer pool on the database instance, right? So the storage nodes, they're up and running, everything is fine. But the buffer pool is cold, so you have to go and ask the storage node for every page until you have your whatever your working set is in memory. Now you have a buffer cache hit ratio of close to 100% again, and then you're off to the races. Then it's fast. So what can you do about this? So now you can see, okay, we had 32 seconds of downtime, right, until we were up and running again. But in fact, you could argue it's like 340 seconds. This is like 5 minutes or so until we were actually full steam. So you could argue we had the less, not fully available for something like 5 minutes. So what could you do about this? Well, this is about keeping the cache warm. So one way to do this would be to say, like, Jimbo, you are incorrect. That's a bad idea. The LSN, the log record that gets sent to the read replica, you should keep that in memory. If you don't find it in memory, why do you throw it away? I keep telling Jimbo, he is wrong. This is bad. But then Jimbo has a counterpoint to this. We should throw it away because on the read replica, sure, you want to fail over to that, but you want to do other stuff with read replicas too. You may want to run some other workload there, some analytical workload or other part of the app, maybe that's read-only runs against the read replica. So the read replica may have a different working set than the primary, right? It needs different stuff in memory. So Jimbo's probably right. Like, we should probably throw that away if we want to use it as a read replica. But what you can do is you can say in Aurora that one of the read replicas should be the failover partner. So if you know that a read replica is a read replica, then you throw away pages that are not in the buffer pool, or sorry, log records that are not in the buffer pool as we send it to them. But if you know that that read replica is our failover buddy, then you want to keep it. So we have those two settings, if you will. So in this case, we have the read-only partner to the right, and then a bunch of, or the failover partner, if you will, to the right, and then the read replicas to the left. So we have something called failover priority. So this one to the right here has failover priority 0, and the one in the middle also, that's currently the master, has 0. And the other folks, they have priority 1, which is worse priority, lower priority. So now, if a crash happens, So now, one thing is we keep sending the information to this to our failover partner, and the difference is if it's not in cache, it will put it in cache. Okay, so it read it and put it in cache. The other thing that happens though is the problem is with the log records, we're only sending writes to our failover partner, right? We're not sending reads. So this person, or I talk about like these are people, they are to me. But it doesn't know about your reads. So you may have done a big table scan and you're happy to have that in the buffer pool, but there was no read that happened on the failover partner, so it doesn't know about it. So the failover partner will go ask the master every once in a while for missing pages. Like, hey, my buffer pool looks like this. What does your buffer pool look like? Oh, it looks like this. And then it can go and request those pages from the storage node. So it tries to keep a hot cache. It would be a little bit behind, but roughly the same buffer pool as the primary for both reads and writes. So now when this becomes the master, it's a hot, it has a hot cache. So now if you look at the same thing, the blue line now, we can see that it was 340 seconds before until we were running, but now it's the same. It's 32 seconds, and we're running at full steam again because we have a hot cache. In terms of recovery time, so this business with the fact that we do the recovery across all of the storage nodes in parallels cuts the recovery time by up to 97%, as this says. So here we have an example based on Sysbench. But you can see in MySQL, this is MySQL, right, Jimbo? Yeah, oh, sorry, Postgres. We keep switching. So in Postgres, in this case, we see examples here where with 3 gigabytes redo, 10 gigabyte redo, and 30 gigabyte redo. And you can see on the x-axis, you have writes per second. So depending on the writes per second, how much time did it take for it to recover? So you can see a larger redo log in this case, on Postgres in this case, will get you a higher throughput, but you also have a longer recovery time in case of failure. And you can see the little guy, or girl for that matter, but in the lower right-hand corner, it's maybe the lower right foot, then, but yeah. You guys very tired. You should. Never mind. It's probably my Swedish humor that's not good. So given that Aurora has no redo, we can have extremely high throughput and extremely low recovery time. So read scalability, again, you have this shared storage. You can create up to 15 read replicas. The redo log replication means that you have very low lag, again, because the redo is almost nothing. Right? The only thing we need to do is throw away or update the buffer pool. We don't need to write. And again, like we saw, you can configure a failover body to make sure that that one also has a hot cache. And by the way, it can be a hot cache. You can still use it for reads. It's just that that buffer pool now is optimized, if you will, to handle the write node's workload. And in many cases, that might be the same. So avoids quorum reads. Yes, so this is just saying that we don't have to read, we don't have to ask multiple nodes about some consensus when we want to read, because the replica knows what LSN it needs from which node. So it goes and asks one in the same availability zone because it would be faster. And if none of the storage, so it asks some storage node, hey, I need page of this LSN, and the storage node may say, I don't have it. Okay, then you can go ask another one. But it assumes the storage node has it. Global databases. So this is one thing we introduced last year, which is basically the ability to have read replicas in other regions. So what we've been talking about until now is that you have these six segments across 3 availability zones, but all of the availability zones are in the same region. So for disaster recovery purposes, you may want to have data in another region. And this, by the way, I think is an important thing for people to think about. This is a very, I think, confusing topic, because a lot of customers I talk to, they talk about disaster recovery, and generally, so there's kind of two ways to look at disaster recovery. It's like how big, what's the range of the disaster, and very commonly, disaster recovery means I replicate to a different building. And so if that's what you mean by disaster recovery, that's what you're trying to solve for, availability zones is good enough, because you are replicating between data centers. So now you need a disaster that takes out at least 2 data centers to have data loss and to have complete unavailability, other than a blip. And so perfectly happy for you to replicate to a different region, which is what we support with global database, but you also pay for that, because now you have to have the storage in that other region, and you have to have the compute nodes and so on and so forth, which makes a ton of sense if what you're looking for, because of your risk assessment, is a complete region going down, meaning 2 availability zones. But a lot of the time, that's not what you need, what you worry about. So many companies or many applications, there are different applications, right? Some applications, super critical, must be replicated all over the place. But some of them are critical, but we don't expect 2 availability zones to go away. Again, 2 different data centers. So then it's overkill to go and do replication across regions. And you can't ask me which ones you should use, because this is up to you, it's your risk assessment. But I'm just telling you, it's a very common misunderstanding that people come and say, I'm going to high availability. So high availability generally on premises means I have 2 machines, right? And 2 storage sets in the same data center, in the same rack even. And you can fail over between those. And then disaster recovery means different building. So again, if that's the definition of disaster recovery, then the existing, what we talked about until now, is good enough. If it's region down, multiple data centers down, then you need something like global database for the disaster recovery use case. There are other use cases also. So in this case, what happens, so we have exactly the same setup as before. Is 5 minutes? Same setup as before. It works exactly the same, but now we have this replication server that is part of it, that you see there in the middle to the left. And the replication server, it owns making sure to send log records, same deal, over to the storage nodes, not the compute nodes, in the other region. And because of the fact that it sends it to the storage nodes, it can do this in parallel. It's not like replication generally is it's one stream. You can stream, if you would, one segment or one protection group at a time. And this, by the way, this replication stream or this replication server is another one that we have to track which LSN that's at. So for example, garbage collection, I can't garbage collect, throw away log records that the replication server needs. So if you think about it, when I want to clean up log records in my primary path, not on S3, I cannot clean up log records that either some other node may need still, okay? Some transaction may need, some reader may need because it hasn't advanced far enough, that the backup, S3 may need it because it hasn't copied yet, been copied to S3, or the global database replication needs. So this is one of the things that the database instance keeps track of, so that we know when it can garbage collect. And then it sends this information down to the storage nodes. They know how far then the volume has advanced and what can be cleaned up, because they're just notified about this from the database instance. Then on the other side, basically the same thing, we have a replication agent that takes all of these streams and just goes and applies it to the storage nodes. And then it's exactly the same code, if you will, as it was on the primary side. Okay? And then you can use this. One is for disaster recovery, like I said. You can fail over to this and make this your primary region. You can also use it to serve reads. So that's another useful thing, is to serve local reads so that you have lower latency. Or you could argue more available needs. So you may have needs this on the east and west coast. And if there is a network issue in between, then these the folks on the other side can still read. They're reading older data, but they can still continue reading. So in terms of replication, this is a very common problem with databases, that if you have a high throughput system, it starts choking, it starts lagging a lot because the pipe can't send it fast enough. So because of the fact that we can run this in parallel, you can see that the replication lag on this right-hand side is still, in this case, the QPS keep going up, so queries per second, and the lag is still under a second. And you can see that the seconds, there's a comma on the right side. So that one keeps under a second. The other one, we're up to 500 seconds in lag. It's a very common problem for MySQL, for example, and PostgreSQL. Perfect. So final thing to mention, we support fast database cloning. I should mention there's a bunch of stuff I can't get to in this talk, but that Aurora can do. For example, we have multi-master. We can have multiple masters writing at the same time, point-in-time recovery, a bunch of things. So I definitely recommend you go onto our website and take a look. There's a lot of talks on YouTube from previous reInvent conferences where you can learn more about Aurora and other of our database offerings. reInvent, by the way, if you're interested, is the first week of December in Vegas. So fast database cloning, this is what you might expect. Is you can tell Aurora, I want a clone of this database. And given now that you have a sense of how the storage system works, creating a clone of a database, we don't actually have to copy anything. We just have a new instance, and it starts on its own log stream. And it can now ask for the log records from the storage nodes, and it can write its new log records. So it can go and diverge now. This is very practical for example, running tests. You can just create a clone, it's almost instantaneous, and then you can go and run any workload, read or write against this clone. But it has diverged, so it will never see the same data as the old database did. It's also interesting, you only pay for the storage, the actual additional storage that you use. So as long as the clone uses the same storage as before, it doesn't modify the pages, you don't pay extra for those. You just pay for the existing storage. So you may have a 50 terabyte database, you create a clone, run some queries and whatnot, you only pay now for the instance that you're running. You don't pay for the storage except for whatever additional storage that you created. Cool. Yeah, this is some comparison just between cloning and Pitter. I think we're at time, though. I got through what I wanted to. I'll stick around, and Jim will stick around a little bit for if you have any questions. But otherwise, hopefully you got a little bit of insight into how Aurora works. Thank you.